So this is the second part of the GSM lecture, and we're going to start off by looking at numbering or identity management in GSM networks. So in GSM numbering, we have two types of numbers. We have numbers that are permanent and numbers that are temporary, and also we have numbers that are associated with the subscriber, and we have numbers that are associated with the communication device. So it's very important in terms of personal mobility to separate the subscriber numbers from the device numbers. So let's have a look at the first category, which is here, which is about numbers about subscribers that are permanent. Okay, so we have something called the IMSI, or International Mobile Subscriber Identity, which is a permanent number. It is a very important number, but it's a number that we want to minimize transmission across the interface, because if somebody was to find a IMSI, then they could find ways of using your mobile services without you knowing about it. And then you have the MSISDN, which is the mobile subscriber ISDN number. This is your dial number. This is the number that you give to your friends and they call you on that. And these are considered permanent numbers because they rarely change. Then we have the numbers associated with the device. Again, each mobile communication device has a number called the IMEI, International Mobile Equipment Identity, and this one is a number that identifies a particular handset. And again, information related to the IMEI is stored in the EIR, and it can be used to block a particular device from being used on a network. Information about the subscribers, such as the IMSI, MSIST, and all those are stored in the SIM card. Now, apart from permanent numbers, we also have temporary numbers. Okay, so we have numbers like TMSI, Temporary Mobile Subscriber Identity, MSRN, Mobile Station Roaming Number, Location Area Identifier, which identifies the current location area where a mobile is currently located, and within that location area identifier you also have a cell ID which identifies a particular cell. So a location area here refers to a group of cells, and a cell ID refers to a particular cell within a location area. So we've talked about the need for separating a subscriber and device information, and we also need to understand that there is a separation between permanent and temporary numbers, so as to for the purpose of mobility management and also security. So let's have a look and go into a little bit more detail. So we've talked about the SIM, subscriber identity module, which stores information about the user services and important user numbers, and one of the most important numbers it contains is the IMSI, International Mobile Subscriber Identifier. So IMSI is a globally unique number. It contains a country code, a network code, and a mobile subscriber identification number. And IMSI is a number that you probably do not know unless you look in your contract, and it's a number that is rarely transmitted across the interface. You want to try and keep that as secure as possible. Now, what the network does, it allocates a subscriber a TMSI. So after your initial attach, that means the first time you switch on your mobile phone, it will transmit the IMSI, but thereafter everything is done using the TMSI, Temporary Mobile Subscriber Identification Number, and this is a number that is allocated by the network, and it is used by the network to identify a subscriber, and it's only valid for a certain period of time. So the TMSI keeps changing, And the next number is the MS ISDN number, mobile station ISDN number, and this is the dial number. This is the number that people call you on, and this is a permanent number. The IMEI number is a number that identifies a handset, and if you open up your mobile phone, at the back of it you will see the IMEI number, and this number is also used to block a subscriber service. The next item that we're going to look at is the GSM interface. So we'll see how a combination of SDMA, FDMA, TDMA and FDD is used on the GSM interface. So let's start off with an axis that represents time. So we have the time axis along here, and we have the frequency axis along here. So along the frequency axis, in the 900 megahertz band, for example, we have a group of frequency 890 to 915 megahertz that is 25 megahertz bandwidth that's used for uplink, and a 25 megahertz bandwidth that's used for downlink. So this 25 megahertz bandwidth is divided into 124 channels, each with a bandwidth of 200 kilohertz, and the same thing on the downlink. So if you allocated a particular channel on the uplink, you'll be allocated the corresponding downlink channel, such that there is a 25 megahertz separation between them. So and this diagram illustrates that. So for example, if you allocated channel 1 on the uplink, then you'll be allocated channel 1 on the downlink. If you allocated channel 120 on the uplink, you'll be allocated channel 120 on the downlink. Okay, and so there is a constant 45 megahertz separation between your uplink and downlink channel. Now within each channel, we divide it into 8 time slots. So this is where the TDMA comes in. So the division of the 25 megahertz into 124 channels on the uplink and 124 channels on the downlink, that is the FDMA aspect of it. The TDMA aspect is on each of these channels, each of these 200 kilohertz channels, we again divide it in the time domain into time slots. So a user gets allocated use of a time slot for communication purposes. The duration of a TDMA frame is made up of 8 time slots, is 4.615 milliseconds, and within this time frame we have 8 time slots, and in each time slot we have we divide it into different parts. So there are parts of the time slot where user data is transmitted, and there are other parts of the time slots where we have to have some kind of a guard space, because of the fact that we have a number of users within a cell using a time slot. So we want to make sure that what one user is transmitting in one time slot does not interfere with information transmitted by another user in the time slot. So we put in some guard space at the end of each time slot to account for that. Okay, so there's a slight correction from the information that's given in the book. Okay, so this red bits represents a correction that you need to be aware of. So essentially in the transmission, so every mobile user, when they allocated a time slot, they transmit a burst, and most of the time they will be transmitting something that is referred to as a normal burst. So there are 3 bits that are reserved for tail bits. There's 57 bits of user data. Then you have an S bit, then you have training bits, 26 bits of training bits, and this is used primarily to ascertain the channel conditions. and then you have one S bit, and then you have 57 bits of user data. So all the user data, whether you're transmitting voice or whether you're transmitting circuit switch data, is transmitted within this. Okay, so altogether we have a total of 148 bits, and this is transmitted. So essentially what we are getting is we are getting a total of 577 microseconds per radio time slot. RTSL stands for radio time slot. Okay, now the last part of the diagram that you see on the bottom right hand side of the diagram illustrates the separation between downlink and uplink. Okay, now we've already seen on the on this part of the graph that there is a separation in frequency, a 45 megahertz separation in the frequency axis between an uplink transmission and a downlink transmission. The diagram at the bottom here says that even in time we separate the uplink and the downlink transmission. Now you might ask yourself, why do we need this separation in time? Well, imagine that you are transmitting on time slot 1, so you'll be allocated time slot 1 on one frequency, and you'll be allocated the same time slot 1 on the corresponding downlink frequency. So it's not possible for you to transmit and receive at the same time. So by separating the uplink transmission and downlink transmission in time, we can use a single radio transmitting device that can both transmit and receive using one radio. If there was no separation between uplink and downlink transmission, you would have to simultaneously transmit on the uplink and receive on the downlink. So to achieve this separation, there is usually a delay of 3 time slots between transmission and transmission on the uplink and reception on the downlink. Okay, so here there is some aspects of TDD. So we've seen how we use FDMA, how we divide the 25 megahertz band into 124 channels of 200 kilohertz each, and we allocate a channel in the frequency domain and the corresponding channel in the downlink, and then we take each one of those channels and we divide it into 8 time slots, and that brings in the TDMA aspect. And then the TDD aspect is in one way it represents the fact that you are separating the uplink and the downlink transmission in the time domain. Okay, now the other aspect, which is the SDMA aspect, is comes in from what we've looked at in the cellular subject. So we'll see that in different cells we allocate different frequencies. Okay, so in this particular example, it's a very hypothetical example. We have frequency 1, carrier frequency 1 being used in this cell, carrier frequency 2 being used in this cell, 3 being used in this cell, and so forth. And this is part of the cellular network planning process, where you allocate carrier frequencies to different cells in such a way that there's minimum interference between adjacent cells. Sometimes you may have a cell in which there is more capacity is needed. For example, there could be a busy shopping center here, or there could be a school here, and so forth. So you would allocate more frequency resources to cells with higher capacity. Okay, so we've already talked about this. So geographical division is divided into areas called cells or sectors, and each cell is assigned a frequency. Consecutive frequency numbers should be separated by a distance so as to reduce interference. And then radio transmission in each cell is divided into 8 time slots, part of the TDMA frame. And then the other important thing that I have not mentioned so far is that usually the first time slot is referred to as T0 time slot, and that is used for the purposes of signaling. and also to increase capacity in a cell, we could allocate several frequencies to a particular cell. Okay, so these time slots that we talked about are referred to as physical channels. Okay, so in the next slide we're going to have a look at something about time slots and how they're arranged. So we've already seen that the most basic unit that is allocated to a user is a time slot, and within the time slot a user transmits a burst, and usually between time slot there is a guard band to make sure that bursts from different users, because time slot 1 may be allocated to a particular user, time slot 2 may be allocated to another user, and we want to make sure that the bursts that are transmitted in these two time slots do not interfere with each other. Now, and we've already seen that the radio time slot has a duration of 577 microseconds, and 8 of these time slots make up a TDMA frame, which has a duration of 4.615 milliseconds. These frames are arranged into something called multi-frames. So here we have a situation where we have 51 frames make up a multi-frame, and then 26 of the multi-frames make up a super frame, and a number of super frames make up a hyperframe. So this is related to how we organize information for transmission. And these have the hyperframe and all the way from the frame, multi-frame, superframe, hyperframe, and they all have certain significance in the network. Okay, so we used the word physical channel before. Now we're going to also look at another term called logical channels. So a physical channel is a time slot. Now sometimes within one time slot we can use it for a number of different purposes, and those would be referred to as logical channels. Okay, so in case of GSM, we have some channels that are referred to as common control channels, and the others are called dedicated channels. So common channels are channels that are common to all users, and dedicated channels are channels that are allocated to a particular user for exclusive use of that particular user. So among the common channels we have broadcast channels. Okay, and broadcast channels are primarily downlink channels because the network is continuously broadcasting information about the network on the broadcast channels. Then you also have common control channels, and these are used to set up a point-to-point communication. So essentially when a mobile is switched on, it listens to information on the broadcast channels, and then the next thing it's going to try and do is trying to grab a common control channel, and once it grabs a common control channel, it's able to communicate with the network and then set up a dedicated channel. So dedicated channels are needed for point-to-point communication, and then once you get a dedicated control channel, you get allocated a traffic channel, and that's when you can communicate. Okay, so the process usually follows reading information in a broadcast channel and then trying to use one of the common control channels, which is common to all the users, to try and get a dedicated control channel. Okay, and once you get a dedicated control channel, you can perform certain signaling with the network and you try and get a traffic channel. Okay, so let's look at these. By the way, these are all logical channels because they all imply partial use of a time slot. So within the broadcast channel, what sort of information is transmitted on the broadcast channels. Okay, so this is primarily a downlink channel. So the network has to inform the users about the carrier frequencies that's being used, and it also, so that's essentially so that you can synchronize in frequency with the network properly. And then the next thing, you also have to do synchronize in time. So we need information about the TDMA frame numbers and so forth. So that is done using the synchronization channel, and then a whole lot of other broadcast information. Say for example, if you're using frequency hopping, what is the hopping sequence that you're using? If when you use paging, you could have paging groups and so forth. So all of this information, FCCH, SCH, BCCH, are all classified as logical channels within the broadcast channel. So every user in a mobile network will be able to listen to this information that are being transmitted on the broadcast channel, and to find out more about a particular network that they have, that the mobile is currently located in. The next set of channels are referred to as common control channels. Again, these are common to all the users. Okay, so sometimes users have to compete for these channels. Okay, so probably the most important one is the RAC channel, random access channel. So random access channel is an uplink channel which users have to contend for, and again they use slotted aloha here to contend for the RAC channel. And a RAC channel is one in which the user requests a service. So for example, when you make a call, you try and send information on the uplink to the network on the RAC, and if the RAC is successfully received by the base station, and the base station has sufficient resources to allocate to the mobile, then an on the access grant channel, which is a downlink channel, the network allocates the dedicated control channel. The dedicated control channel is allocated using the access grant channel. Okay, so and you also need common control channels for paging, and this is a downlink channel where a network tries to contact a user within a location area to find out information about the user, so as to be able to connect an incoming call to a mobile subscriber. So if you look at the step, a user, when you switch on a mobile in a network, it goes through information in the BCH, and once it has read and understood the information in the BCH and it's got itself synchronized in frequency and time to the network, then the next thing it tries to do is tries to send a request using slotted aloha on the RAC, and when it gets a response on the AGCH, it is now able to get a dedicated control channel which is dedicated for that user, but it's still a control channel, and the dedicated channel is the one it uses to try and get a traffic channel. Okay, so in the traffic channels we have different possibilities. The TCHF is the full rate, so this corresponds to about 13 kilobits per second. This is where you have full use of a time slot. Okay, and this is probably the best resource a mobile subscriber can get for making a circuit switch call. The other possibility is to get something called TCH half rate. So this is a case in which user only gets use of half a time slot. Okay, so that means maybe two users are sharing the use of a time slot, but the communication will still be intelligible. And then you also have the TCH-EFR enhanced full rate, and this provides better speech quality than the TCHF. Now, in order to get this traffic channels, a user has to first get something called the control channel, which is referred to as SDCCH, which stands for Slow Dedicated Control Channel. And this is the access. When you get a request on the access grant channel, you get allocated an SDCCH, and the SDCCH enables you to signal and set up a traffic channel. So these are the important channels, and as I said before, these are all logical channels, because for transmission of almost all of these channels does not require a physical channel. Okay, so you can have all of these broadcast channel, common control channels, all being transmitted on time slot 0, and you'll have some traffic channels and some dedicated control channels being transmitted on a particular time slot. Okay, so now that we have an idea of how the air interface works, we can go and see how does the GSM network operate. So in particular, we'll be looking at session management. So how is a session set up when you make a call? Okay, so there's a number of different signals that have to be sent across the network before a call can be established, and the timing diagram here tells you how that is set up. So here we're going to look at a mobile originated call. So this is a call which originates from a mobile, and what happens here in a mobile originated call, so essentially you send a channel request from the mobile station to the BTS. So that's represented by number 1 here. So this is done on the RECH, and the base station looks at the request and says, do I have enough resources to accept this call? And if it does have any resources, if it does have resources, it will send an assignment request, and this is done on the access grant channel, okay, on the downlink access grant channel. Okay, and the thereafter on the access grant channel, you also get allocated an SDCCH, and on that SDCCH, the mobile subscriber will then send a service request. Okay, so when that service request is sent, what happens is it goes all the way up to the MSC, and the MSC then has to do a security check. So it goes up to the VLR and finds out certain parameters about this particular subscriber. So, and from those parameters, it's able to do an authentication request. So an authentication request is sent from the MSC through to the MS mobile subscriber, and the authentication request has an authentication response, and based on the response that is received by the network decides, okay, this subscriber is authenticated now, and then thereafter, now that the subscriber is authenticated, we can now start ciphering. That means everything that is sent across the interface will be encrypted so that nobody else can listen to it, and once that is done, the call starts beginning. The call setup information is transmitted, and then it's confirmed, and once the call is confirmed that the called party is available to take the call, then we start allocating resources, radio resources. So that is essentially a time slot or partial use of a time slot for a particular call. So these are so quite a lot of signaling has to take place in a network even to set up a simple voice call. The second diagram is for a mobile terminated call. The mobile terminated call is a little bit more complex than a mobile originated call, because a subscriber, the location of a subscriber is only known at something called a location area level. It's very complicated to keep track of every subscriber at cell level. So the designers of most mobile networks know the location of a subscriber at the location area level. So a location area is essentially a group of cells. So when a call is received for a subscriber, and this might be a call that's coming from a PSTN network, it comes to the GSM gateway MSC. Gateway MSC is a MSC in a network that connects to an external PSTN network. So at that point, the GMSC contacts the HLR, and it requests the MSRN, which is the mobile subscriber roaming number. And once you have the mobile station roaming number, you also know which is the MSC that is currently serving the subscriber. So the call is then moved to the serving MSC. The serving MSC then has to find out where the subscriber is located. So it sends a message to the BSC. The mobile MSC also has information in the VLR about which location area currently a subscriber is located in. So it sends a message to the appropriate BSS. And what the BSS does then is it pages for the mobile subscriber in all the cells associated with the location area. And when a mobile subscriber answers that request, the call is switched through to the appropriate BTS. Okay, another thing that a GSM network has to do is mobility management. So as a subscriber moves around in the network, handovers have to take place. So how is that done? Well, there are different types of handovers. Sometimes a mobile subscriber could move from one sector to another sector within the same cell, or it could be from one cell to the next cell. So two different BTSs but the same BSC. And it's also possible that a subscriber moves from one cell to another cell, which are in two different BTSs and are also served by different BSCs. And the fourth case is where you're moving from one cell to the next cell, which have a different BTS, a different BSC, and a different MSC. This one here would be number 4 would be the most complex of the handovers. So in terms of handover, what is exactly happening? Well, how do we know? How does a network know when a handover has to be performed? Well, what happens in every mobile is that mobiles are measuring the radio signal strength of the serving BTS, but also other BTSs in the neighborhood. And these measurements are being sent across the network, and they're being handled by the BSC. So let's consider the case that a mobile subscriber is moving from one base station away from the serving base station to another base station. So you see that the received signal strength from the base station will be dropping, and the received signal strength of a neighboring base station would be increasing. So and at some point you have to do a handover. So the question is, at which is the best point to do it? Now if you perform the handover somewhere close to this, you can see that because of the radio and the rapid variation of radio signal strength, you might continuously be handed over from the old to the new, back to the old base station. So that is referred to as the ping pong effect. So what we do is we do not do a handover at this point, but we do the handover further up based on something called a handover margin. So it's only when the new BTS signal strength is above the or by a handover margin that we perform handover operation. Okay, so handover also requires a number of signaling messages to be sent across the network. So as I mentioned earlier, the mobile station is continuously transmitting measurement reports to the BTS, and the BDS transmits it to the BSC. And since all handover decisions are performed at the BSC level, the BSC says, okay, this is a good time to make a handover because radio signal quality is very poor to the old base station, and it will send a request to the MSC saying, look, we want to perform a handover. And sometimes you may be transferring from one BSC to another BSC, so that handover request has to be sent to the new BSC, and this new BSC must have sufficient resources to allocate to the handover call. And if it does, then a channel activation message saying to the appropriate BTS that is serving the relevant cell will be sent, and then a call is set up. Okay, so let's move on to the next aspect, which is the security aspect in GSM. So we talked about the fact that there are different authentication and encryption mechanisms that are used in GSM, and we'll have a look at those a little bit more detail in the next couple of slides. So what are the important security services that GSM provides? So the first one is access control, and access control is about there's one aspect of access control is accessing the handset. So usually there is a PIN number associated with accessing the handset, and then the next one is we want to make sure that the SIM is properly authenticated, and we have a challenge and response method that is used to do that. The second aspect of security is confidentiality. So that means nobody should be able to look at your data which you're transmitting across the GSM network. So for that purpose, voice and signaling are encrypted over the air interface. And a third aspect of security is anonymity. So this is to do with the IMSI. We said the IMSI is a very important piece of number, and we don't want to transmit that across the interface, or we want to minimize the transmission of IMSI. So we have the TIMSI that is used for this purpose, and it has a time period associated with it, and every time you do a new location update, the TIMSI is changed. In terms of algorithms, there are three important algorithms from the point of view of security. We have something called an A3 algorithm, which this is a well-defined algorithm, and this algorithm is kept both in the authentication center as well as in the handset, more specifically in the SIM card. And you have the A5 algorithm, which is used for encryption. Again, encryption is performed between the mobile equipment and the base station. And we have the A8 algorithm, which is used for generation of keys that are used for authentication and encryption. So here's a diagram that shows how authentication is performed. So the important aspect to the authentication is a key called KI. Okay, so this key KI is stored in the authentication center and in the SIM card of the user. These are the only two places on the network where this key is stored, and this key is the key to your security basically. So it's a 128-bit number, and the authentication center uses this key and a random number that it generates, and that goes into the A3 algorithm, and the A3 algorithm produces something called a signed result. Okay, and so the only way, as I said, the A3 algorithm is a well publicized algorithm, everybody knows about it. The RAND is also not so confidential, but a confidential piece of information is this security key. So when you are making a call, for example, what happens before you have to authenticate a subscriber? So the network element, the MSC, has associated with it the RAND and the signed result. Okay, now the only way you can get this signed result is if you know the key, and because the key is only stored in two places, in the authentication and the SIM card, nobody else should have access to this particular key. So what the network does is it sends this RAND number across the interface to the user during the authentication process, and using this RAND, the SIM card generates a signed result and sends it back. And all the MSC then does is it checks if the signed result that the authentication center generated matches with the signed result it has received from the user. And if it does, that means it must be from someone who knows the key, which is a very confidential piece of information. So that's how authentication is performed. Okay, and every time you do an authentication, you may be sending a different RAND number. You don't have to send the same RAND number. It does not make sense to send the same RAND number, because once someone has observed the RAND and the signed result, they could use the same signed result again. How does the encryption work? Again, encryption in some ways is very similar to the authentication process. So again, we use the same secure key KI and the same RAND that was used for the authentication process, but this time these two inputs go into an A8 algorithm, and the A8 algorithm generates a 64-bit key, and this 64-bit key is then sent to the BSS, and in the BTS specifically, all the data that is transmitted across the interface is encrypted using the A5 algorithm. So the key KC, which is generated from KI, is the key for encryption, and the only way you'll be able to generate the cipher key KC is if you had access to the subscriber key KI. Another aspect of GSM is HSCSD. So HSCSD is a technology that improves or increases the data rate available on GSM, and the way this was done was by putting together a number of time slots together. So we know that if you have one time slot, you can achieve about 9.6 kilobits per second, and with better coding you can get 14.4 kilobits per second. Now this rate was still very low for internet or multimedia applications, and so they came up with the idea of HSCSD. So, and this was possible by using software updates, and that was one of the good things. Without doing any hardware changes in the network side, you were able to offer this. Obviously you needed new handsets that could that could support HSCSD, but the basic idea behind this is that instead of allocating one time slot to a user, we allocated a number of time slots. So in the case that a user gets allocated a number of time slots, say if you are working with the basic 9.6 kilobits per second, you could achieve 19.2 kilobits per second if you allocated 2 SLAM slots or 3 time slots and so forth.